Hello everyone, I Rabia Kamra welcome you all to the 7th lecture of the course Calculus and ODEs. In today's lecture we will discuss absolute convergence and conditional convergence, that is section 8.7 from the book Calculus and Analytic Geometry by Thomas and Finney. So let us first define absolute convergence. A series summation an converges absolutely, or we say it is absolutely convergent, if the corresponding series of absolute values, that is summation mod of an, converges. So what we are saying, that we say that this series an converges absolutely if you take the absolute value of each term of the series, and if this series turn out to be convergent, then we say that this series summation an converges absolutely. Let's see with an example. So consider this geometric series. So this series 1 minus 1 by 2 plus 1 by 4 up to so on. So we see the common ratio R of this series is minus 1 by 2, and since mod of this is strictly less than 1, this geometric series converges. Now the question is this geometric series converging absolutely? So for that, what we will do, we will take the mod of each of these terms. Take the absolute value of each of the term of the series. So when you take the absolute value, the corresponding series of absolute values will be this series, right? Again, a geometric series with common ratio R 1 by 2. This is also less than 1. So we say that series of absolute values corresponding to this series is also converging, and hence we say that this geometric series converges absolutely, right? One more time I'm telling you that we say that this series summation an, this converges absolutely if the corresponding series of absolute values, so you take the series of absolute values, if that also converges, we say that the original series, this one, this converges absolutely. And in this example, we saw that this geometric series converges absolutely. Now see this example, the alternating harmonic series. In last lecture, we proved this alternating harmonic series is convergent by Leibniz theorem, where the three conditions given in the Leibniz theorem was satisfied, and then we say that the alternating harmonic series converges. So we know that this series converges. Now the question is, does this series converge absolutely? Is the corresponding series of absolute values, is that convergent? So what will be that series? This series, right? When you take the series of absolute values, it will turn out to be this series. Now this is a harmonic series and it is a divergent harmonic series. We proved this by P series test, which says that when P is greater than 1, in that case this series 1 by n to the power P converges, and when P is less than equals to 1, this series diverges. So we can say that this alternating harmonic series, this converges, but when you consider the corresponding series of absolute values, it turns out to be 1 by n and it diverges, right? So we can say that this alternating harmonic series does not converge absolutely, right? The corresponding series of absolute values is not converging, and hence the alternating harmonic series does not converge absolutely. With this, we have another definition, which is conditional convergence. Now, what is conditional convergence? A convergent series that is not absolutely convergent is conditionally convergent. So what we are defining, we have a series which is a convergent one. We have a series, suppose here we have this series, a convergent one. Then you consider the series of absolute values. Now this series is not convergent. So we say that this series converges conditionally. For example, in this series only, this is a convergent series, but the corresponding series of absolute values, that is not convergent, right? So we say that this series is not absolutely convergent, but this series is conditionally convergent in that case, right? So we call such series where the series is convergent, but it is not absolutely convergent. We call them as conditionally convergent. Okay, so see, you have this series, this one. So till now we did two cases, that either this series converges or this series diverges. Now we have considered further two cases. If this series converges, then does this converge absolutely or it converge conditionally? We say it converges absolutely if, when you consider the series of absolute values, that also converges, we say it converges absolutely. If the series is converging, but the corresponding series of absolute values, that is diverging, we say that this series converges conditionally. Okay, I hope it makes sense now. So either the series is convergent or divergent. Then if it is convergent, it could be absolutely convergent or conditionally convergent. We say it is absolutely convergent if the corresponding series of absolute values, that turns out to be convergent. We say that the original series is absolutely convergent. If for the convergent series, the corresponding series of absolute values turns out to be divergent, we say that the original series is conditionally convergent. Next, now the question is, we have already discussed the convergence and divergence of series, and we have developed some tests also to check their behavior. Then why do we need absolute convergence, right? So very important question. Because whichever test we have developed in last three sections, you remember integral test, ratio test, comparison tests, and nth root tests, all those tests were developed for series of non-negative terms or for positive terms, right? So since we already have good tests of convergence of series of positive terms, so whenever you have a series, this one, where you have this series as the terms containing both positive terms and negative terms, means we are saying that this series could have any type of terms, positive or negative. So it makes sense to consider the absolute value of this series. And now when you take the absolute value, all the terms are positive, and hence you can apply all those tests that we have developed so far, right? Next is a very important reason is that if a series converges absolutely, then it converges. Means if I prove that this series converges absolutely, it proves that this series is convergent. So if you're asked to test the convergence of a series which has both positive and negative terms specifically, in that case, first thing, if the series is alternating series, means you have 1 plus 1 minus 1 plus 1 minus type of terms, then you can go for Leibniz test. If the series has 1 positive, 2 negative, or if there is no trend but the series has both positive and negative terms, in that case, what can you do? Take the series of absolute values, test its convergence. If this turns out to be convergent, then we can conclude that the original series with both positive and negative terms which it has, this series also converges because of this theorem which says that if this series converges, means we are saying that if this series converges absolutely, then this series converges. Here your n varies from 1 to infinity. So the same theorem can be rephrased as that every absolutely convergent series converges. Means if a series is absolutely convergent, or if a series of absolute values is converging, then the series converges. So this absolute convergence test will help us to test the convergence of many series which have positive negative terms. However, the converse of this theorem is not true. This is a one-way theorem. If this series converges absolutely, then this series converges. But if this series converges, it may not be the case that it is absolutely convergent. Of course, we did conditional convergence case, right? If this series converges, but the series of absolute terms, that is not converging, so we call them as conditional convergence. So note that the converse of the above statement is false. There are many convergent series that do not converge absolutely. One such example is alternating harmonic series. Alternating harmonic series is convergent, but it do not converges absolutely. Right? So let's use that test along with the results which we have discussed so far. So test the convergence of this series. So you are given this series. See, there's a proper pattern, one positive term, then one negative term, one positive, one negative. So you can also go for the Leibniz test. Okay. You can go for the Leibniz test, no problem. In that Leibniz test, this will be your UN, and you see whether the three conditions are satisfied. Then you can conclude the convergence. Other way is, since you have this series and we know this result that if this series converges, it implies that this converges. So we will use this result here. Consider the corresponding series of absolute values. So what will be the corresponding series of absolute values? It will be this series, summation n going from 1 to infinity, 1 by n to the power 2. Now here, when you apply p test, your p is equals to 2, which is strictly greater than 1. Right? So this series converges by p series test. So since this series summation of mod of an converges, we can conclude that this original series, summation n going from 1 to infinity minus 1 to the power n plus 1, 1 by n square, this converges. So we say the series converges absolutely and hence converges. So we'll see next example. Test the convergence of the series summation n going from 1 to infinity sin n upon n square. So we have this series. Now note here that sin 1 is a positive number, considering that this is in radians. Sin 1 will be a positive number, but eventually sin 4 will be a negative number. So in this series will contain both positive and negative terms, because sine function, the value of sine, will lie somewhere between -1 to 1. So we have to test the convergence of this series. So you cannot directly use the tests you have done so far, right? The test that you have done so far for the series of non-negative terms, that you cannot use for now, right? But you can use those tests once you consider the series of absolute values, right? So consider the corresponding series of absolute values. So you have this series. Now in this series, each and every term is a positive term. Now you can use all the tests we have discussed so far for the series of positive terms or non-negative terms. So when n is equals to 1, this is sin 1 by 1 square, the first term. Second term is mod of sin 2 upon 2 square plus mod of sin 3 by 3 square, and keep on going like this. Now you see, that since sine is a bounded function, mod of sine n will always be less than equals to 1 for every value of n. So we can say that this quantity is going to be less than equals to 1. And likewise, this quantity is going to be less than equals to 1 by 2 square, and we keep on going like this. So we have this whole series, this is less than equals to 1 plus 1 by 2 square plus 1 by 3 square plus keep on going like this. Now this is a p series. For p is equals to 2, this is this series basically. Summation n going from 1 to infinity 1 by n square. Now this series converges by p series test, right? So what we have now in hand is that this series is less than equals to this corresponding series, and this series summation 1 by n square is a convergent one. So we can say that this series summation n going from 1 to infinity mod of sine n by n square, this converges by comparison with this one. So we are using a comparison test here, right? Now this series is less than equals to this series, and this p series converges, hence we conclude the convergence of this series. Now if this series is converging, we can conclude that the original series converges absolutely, right? Means the original series converges absolutely, and hence it converges, right? So we have concluded that the original series converges. Let's see next example. Alternating p series. So we have this summation n going from 1 to infinity minus 1 raised to the power n minus 1 upon n to the power p. So this is a p series with alternating positive and negative terms, and p is strictly greater than 0 here. Now we want to test the convergence of this series. So the first method is to go for Leibniz theorem. Since you have proper alternating series, you can apply your Leibniz theorem. So this is basically 1 upon n to the power p is your un, right? So un is 1 by n to the power p. So see that this un is going to be a positive quantity for all values of n, because here p is a positive constant, right? So we can say that the first condition of the Leibniz theorem is satisfied, that uns are all positive for all values of n and p greater than 0. And the second condition, that un should be greater than equals to un plus 1, that also holds, because 1 by n to the power p is always greater than equals to 1 by n plus 1 to the power p for n varying from 1 to infinity. So we say that the second condition of the Leibniz theorem, that is also true. The third condition, that this limit as n tends to infinity should tend to 0. So 1 by n to the power p tends to 0 as n tends to infinity. So we can say that by Leibniz theorem or by the alternating series test, this alternating p series converges. Okay. Now that we have concluded that this series is converging, next we want to see that for which values of p it converges absolutely, and for which values of p it converges conditionally. So for now we have this case, p is greater than 0, right? And what we know about the p series is this series 1 by n to the power p for p greater than 1 converges, and for p less than equals to 1 diverges. This we know. And this also we know that this alternating series converges for p greater than 0. Now consider the series of absolute terms. So when you take the absolute value, you have series of absolute terms will be this one. Now look at this series, the series of absolute terms. This will be convergent for p greater than 1. It means that for p greater than 1, the original alternating p series that converges absolutely, right? And when p is less than 1, the series of absolute values, this turns out to be divergent. It means that when your p is less than equals to 1, this original alternating p series, this is conditionally convergent, right? So we have for p lying between 0 to 1, 1 is included, the series is conditionally convergent, alternating p series. And for p greater than 1, the alternating p series is absolutely convergent. Now look at this example. Suppose you are asked to test the behavior of this series. So look at this series. This is an alternating series. Also, this is a p series with p is equals to 1 by 2. So you can directly conclude that by alternating p series test, since p lies in here, we can say that this series is conditionally convergent. And what about this series? In here you have p is equals to 3 by 2, which is this case. P is greater than 1. So we say that this series converges absolutely. Right. So next is, given this problem, you have to check whether the series is convergent, divergent, it converges absolutely or conditionally, and give reasons for your answers, right? And sometimes when we prove that a series, you test the convergence of the series and you prove that the series is converging absolutely, then at times we need not to write that it is convergent, because absolutely convergent implies convergent, right? But if it is asked that answer should be whether the series is convergent or divergent, in that case you have to conclude that since the series is absolutely convergent, it implies it converges. Now see this example, summation n going from 1 to infinity minus 1 raised to the power n plus 1 into 0.1 raised to the power n, right? So we have considered the series of absolute values. So considering the absolute value, we have this one, 0.1 raised to the power n. So this is the series. Summation n going from 1 to infinity, 1 by 10 raised to the power n. Now this is a geometric series. A geometric series whose common ratio r is equals to 1 by 10, which is strictly less than 1. So we say that this is a convergent geometric series. Now since this is a convergent geometric series, we can conclude that this series converges absolutely. Or one can also write this series converges, and hence it implies it converges. So we can say that the given series converges absolutely. Now this is the series given, summation n going from 1 to infinity minus 1 raised to the power n plus 1 n factorial by 2 to the power n. Now we are going to apply the nth term test for divergence here. So you see what is the limit n tending to infinity of this term n factorial by 2 to the power n. Now when you take the limit of this one, look at the numerator. Numerator is n factorial and denominator is 2 to the power n. Now as your n increases, out of the numerator and the denominator, which quantity will grow faster? Right? So here we can see that the growth of n factorial is faster than growth of 2 to the power n as n increases. So we can say that the limit n tending to infinity of this quantity will tend to infinity, right? So by nth term test for divergence, since this limit is infinity, we can say that this series diverges, right? So when you find the limit n tending to infinity, suppose if you consider this quantity also alongside, in that case you will have plus minus infinity. So that does not make any difference. Now, next is rearranging a series. Now, we know that if you have a series which has a finite sum, suppose we have proved that the series has a finite sum, then of course we can rearrange the terms of the series of a finite sum, right? Suppose 1 plus 2 plus, suppose you have this series summation 1 by 2 to the power n. So it is a geometric series which converges, and you also know the sum of the series. So since this is a convergent series, you can rearrange the terms. In that case also it will remain convergent and it will converge to the same finite sum. Now the question is, if you have an absolutely convergent series, in that case, can you say that any arrangement of the terms of the series will not change the behavior of the series? That is the rearrangement theorem for absolutely convergent series, which says that if you have this series and you know that this series converges absolutely, right? So this series was constructed from this sequence whose first term was A1, then second term was A2, then third term was A3. This series was constructed from this sequence, right? Now suppose you have some other rearrangement of this sequence. Suppose you are calling your A2 as B1. This is the first term of the sequence. Say some A10 as your B2, and basically I am saying that you have rearranged this sequence into this another sequence, and you have constructed a series out of this sequence, summation Bn. In that case, can you say that this series and this series are converging to the same sum? Yes, we can say that any rearrangement of this sequence will result into some series. If this series is absolutely convergent, then this rearranged one, the series which is constructed from a rearranged sequence, that will also converge absolutely, and their sum will also be equal. Now another question I want to pose over here is, suppose here you do not have absolutely convergent series. Suppose you have conditionally convergent series. Can you say the same result in that case, that they will both converge absolutely and their sum will be equal, or they both converge conditionally and their sum will be equal? So next we want to address this question, that can we rearrange the terms of a conditionally convergent series and yet get the same answer? So the answer is no, we cannot arrange the terms of a conditionally convergent series. If we rearrange the terms of a conditionally convergent series, we will get different results. So let's just see this with an example. Let's see this example. So we are given this series, summation n going from 1 to infinity, minus 1 raised to the power n plus 1, 1 upon n square. Now you know that this series converges by Leibniz test, and this series converges absolutely by P-series test. So we have that this series converges absolutely. Now we can say that the rearrangement theorem for absolutely convergent series can be applied over here. We have summation an which converges absolutely, and now we will take any other arrangement of the sequence an, and that should also turn out to be absolutely convergent. So you see, a possible rearrangement of the terms of the series is 1 minus 1 by 4 minus 1 by 16 here as a third term, then 1 by 9 plus 1 by 25 plus 1 by 49, these three positive terms, then these negative terms. So what way we are doing? 1 positive terms, then 2 negative terms, then 3 positive terms, then 4 negative terms, then 5 positive terms, and we keep on going like this. So this is one possible rearrangement that we have considered. Now, since the original series for which we have taken this rearrangement, since the original series converges absolutely, so the rearrangement theorem says that both series converge to the same value. This is coming from the rearrangement theorem, that if this series converges to some number L, this rearranged series, this should also converge to the same number L. And how can we write the sum of the either series? Now look at this series. This series we wrote like this: minus 1 raised to the power n plus 1, 1 by n square. Now when we have rearranged it in this manner, we can write this series as summation n going from 1 to infinity 1 upon 2n minus 1 whole square minus summation 1 upon 2n whole square. Now you see, when you substitute n is equals to 1, you have your first term, right? When you substitute n is equals to 2, so you have 1 by 9. When you substitute n is equals to 3, you will have 1 by 25. When n is equals to 3, 2 3s are 6, minus 1 5, 5 square is 25. So these positive terms are coming from the first part of this series. And for the negative term, see, when you substitute n is equals to 1, you have 1 by 2 square, that is minus 1 by 4. Then when n is equals to 2, you have 1 by 4 square, that is minus 1 by 16. When you substitute n is equals to 3, so 2 3s are 6, 6 square is 36, so this term will come, right? So a rearrangement of the terms of this series has resulted into the another series, and by the rearrangement theorem we can say that both the series will converge to the same value, right? Now we will consider a series which is conditionally convergent. Now see this series, we know that the alternating harmonic series converges, right? But we know that it do not converge absolutely, it converges conditionally. That also is a fact, right? Now since this series converges, we say that it converges to some number L, right? Moreover, by alternating series estimation theorem, we can say that this number L, the limit to which this is converging, this lies between any two successive partial sums. We said that L is going to lie between Sn and Sn plus 1. This is what we said, whichever is bigger. So here you have Sn plus 1 or Sn also, right? So since S2 is 1 by 2 and S3 is 5 by 6, S2 is the sum of first two terms. So first two term, this series 1 minus 1 by 2 plus 1 by 3, like this. So the S2 is 1 by 2 and S3 is 1 by 2 plus 1 by 3, 5 by 6, right? Since S2 is 1 by 2 and S3 is 5 by 6, so L cannot be 0. Right? L has to lie somewhere between 1 by 2 and 5 by 6. Right? L will lie somewhere between. So L cannot be 0. Now what we are saying is multiply this series by 2. So we have, if this series, sum of this series is equals to L, we have 2L is equals to this series multiplied by 2. Right? So 2 times of this series is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and we have written around 12 terms, 11, 12 terms. Now multiply this 2 with the whole series. So this is 2 minus 1 plus 2 by 3 minus 1 by 2 plus 2 by 5, going on like this. So this series, twice of this is basically this series. Now we are going to rearrange this series, right? So rearrange this series as this is 2 minus 1, 1. Then this term, writing this, not writing it on the fourth place, writing it on the third place, that is a rearrangement basically. So minus 1 by 2 here. Then the terms whose denominator is 3. So this is 2 by 3 minus 1 by 3. Then this term whose denominator is 4. Then this term 2 by 5 and minus 1 by 5 whose denominator is 5. So we have collected them like this, rearranged them in this way. So this first term is 1, then minus 1 by 2. Then this term will turn out to be 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6. So basically when we have rearranged this series, it has turned out to be this series only, minus 1 raised to the power n plus 1 into 1 by n, the harmonic series. And we know that sum of this harmonic series is L, right? So we started with 2L, and after a rearrangement we have reached at L. So by rearranging the terms of a conditionally convergent series, this series, twice of the harmonic series we considered, the series become this alternating harmonic series. So if the two series are same, so initially this is basically 2L and this is L. If these are same, it means 2L has to be equals to L. But clearly this cannot be the case, because they could be equal only if L is equals to 0. But in our case, L is not equals to 0. Right? So we have reached at a contradiction. So the thing here is that the rearrangement of terms changes the behavior of the series if the series is conditionally convergent. Rearrangement will not make any effect if the series is absolutely convergent. If we rearrange the terms of a conditionally convergent series, we can get results that are different from the actual sum of the original series. That is what has happened here, right? Because the series with which we started, this was not absolutely convergent series. This was a conditionally convergent series. And when we did some manipulation on this series by rearranging the terms of the series, we have reached a contradiction. So we can say that the last example shows that we cannot rearrange the terms of a conditionally convergent series, right? And we cannot expect that the rearranged series to be the same as the original series. If the series is conditionally convergent and you are changing or rearranging the terms of the series, you will have a new series which will be altogether different series. It won't be the same series as the original one, right? So when we use a conditionally convergent series, the terms must be added in the order they are given. Yeah, you are not allowed to change the order. You have to consider the same order in which they are given to obtain a correct result. To the contrary, the rearrangement theorem guarantees that the terms of an absolutely convergent series can be summed in any order, right? Whereas when you have a absolutely convergent series, you can sum up them in any order. That won't affect the final answer, right? The sum will remain the same. Okay, so this was about rearranging the terms of the series. Now we just summarize all the tests that we have done so far, that given a problem, in which direction you should work so as to conclude the convergence or divergence or absolute convergence or conditional convergence of the series. So the first thing given a series is every time we apply the nth term test, because if the nth term test limit of an as n tends to infinity turns out to be a number not equals to 0, we can conclude the divergence of the series, right? That is one important thing we every time do. Given a problem, we try to apply the nth term test for divergence. But point here to notice is that nth term test for divergence will only conclude the divergence of the series. It would not say anything about the convergence of the series, right? So given a series, we see if this limit is equal to 0, if this is any number not equals to 0, or if does not exist, it does not exist, we say that series diverges. Suppose it turns out to be equals to 0. In that case, the series may or may not converge, right? Now, if this happens, if this limit turns out to be 0, after that you have to gauge the terms of the series. That is there a specific pattern? Is it a geometric series? Is it a P series? Is it an alternating P series? Or it is an alternating series? So gauging the type of the series, we can decide that which test we should apply. So if it is a geometric series, in that case, you see that if it is of this form, If it is yes, then we say that whenever mod of r is strictly less than 1, this series is going to converge and it will converge to the number a upon 1 minus r. And if this mod of r is greater than or equal to 1, the series diverges. Next is if the series is of the form 1 by n to the power p. If it is a p series, you see if p is greater than 1, series converges. If p is less than or equals to 1, series diverges. If it is not of this form also, then what can you do is you can consider the series of absolute values, and now when you have the series of absolute values, the terms are all non-negative, so you can apply any of the tests that are developed for series of non-negative terms to conclude the convergence of the series. If you take the series of absolute values and it turn out to be convergent by any of these tests, we can say that the original series converges, because the series is converging absolutely, which implies the series converges. Suppose suppose you do not apply this test or the series for absolute terms. If you do not consider the series with the absolute terms, then you see that is there a proper trend that you have a positive negative term. In that case, if it's an alternating series, you see whether the conditions given by the Leibniz theorem are satisfied. If yes, they are satisfied, we conclude the convergence. If no, if they are not satisfied, then you have no option and you have to go for the sequence of partial sums. Consider the sequence of partial sums, and from there you could conclude something, or we need some more tests for this, right? But for the examples that we are discussing, it will fall into any of these category and you'll be able to apply any of these tests. Okay, so this is the summary and that's it. Thank you. Have a nice day, everyone.